Hello and welcome to today's session. So today we are going to discuss on a silicon controlled rectifier. So silicon controlled rectifier is somewhat similar to our normal PN junction diode, where it allows the current to flow in one direction, that is from anode to cathode. But the silicon controlled rectifier has its own range of applications, which is used in high power applications to control the power of and the current which is flowing in one direction, or it might be used in the conversion of DC to AC. So likewise, it has got a wide range of applications in power amp in we can say that in case of uh, power applications, high power applications. So now we will look into the construction of the SCR. So construction of SCR is somewhat looks like similar to the transistor, but transistor is this is a transistor where it has three layers and two junctions and three terminals, that is emitter, base and collector, whereas the SCR, the silicon controlled rectifier, has the four layers, that is PN, PN and three junctions, that is J1, J2 and J3, we can name it like this. And we need two types of material to construct these SCR, that is P-type material and N-type material. Yes. And the right hand side, you can see the symbolic representation. It looks like similar to the diode, but there is one more controlled terminal, that is the gate terminal. Okay, so this is the first terminal, we call it as anode, and the second terminal is cathode. So it means the high current flows from anode to cathode, and to turn on the SCR, there is a gate current is required to turn on the SCR. So SCR is made up of a silicon, so that is why it is named as a silicon controlled rectifier. So now if you see this SCR, it has the three junctions, and the gate terminal is connected between the two junctions, that is J2 and J3. Now if you look into the SCR construction, we can also model the SCR construction with the help of two transistors. So we will be using the two transistors, that is PNPN and NPN transistor. So whereas the first transistor I will call this as T1 and the second transistor I will call this as T2. So the base and the emitter of PNP and NPN transistor are shorted together, and the collector of T1 transistor is shorted with the base of T2 transistor, and the emitter of T1 transistor we call it as anode terminal, and the collector terminal of T2 transistor we call it as a cathode. And that forms, it means by using the two transistor we can model a silicon controlled rectifier. So this is about the construction of the silicon controlled rectifier. So let me save this graph. So let me call this as page 12. So after this, we will look into the characteristic graph of this SCR. How does it work? Now, if you see from this SCR, when we apply a positive potential at this point and negative potential across the cathode, so what happens? This first junction is forward biased and this J3 junction is forward biased, whereas if you see this, the J2 junction is reverse biased. Due to this reverse bias condition, what happens? This SCR will remains to be in an off state. To turn on the SCR, we have to give the gate current. Until unless we'll give the gate current, the SCR will not be turned on. So there are few properties of this SCR. To turn on this SCR, we have to apply the gate current, sufficient gate current, so that the SCR will be on. And once the SCR is on, the gate current has no significance in the sense of controlling this SCR or to make the SCR off. Even if we turn off this gate current, SCR will remain to be in an on state. So that we will explain in the characteristic graph. So let us take the characteristic graph of SCR. So let me plot this characteristic graph. So this is V and this is I. The x-axis is the voltage and y-axis is the current. So now as we increase the voltage without the gate current, it requires a very high anode to cathode voltage, and at some point maybe 300 volts or more than 300 volts is required to turn on the SCR. and once we reach that breakdown point or the conduction point, the till that point the current is very small, and suddenly when it enters in the conduction mode, the voltage suddenly drops to a very small value. Because it is a silicon, we know that the silicon, the cut-in voltage or the cutoff voltage is 0.7 volt, so it will suddenly drop to a very small voltage, and thereby the current suddenly starts increasing like this. And this current we call it as IH. So IH stands for the holding current. So this current we call it as IH current. And as we apply the gate current, this might be for the gate current IG is equal to 0 milliamperes. And then as we apply the gate current, then the it will start conducting for the lesser voltage of anode to cathode, and then it starts conducting. So likewise, if you see, as we increase the gate current higher and higher, for the lesser anode to cathode voltage, the SCR will turn on, and thereby the SCR will be in the on state. So this might be for, this is for say IG1, this is for IG2. So the IG1 and IG2 are the higher gate current. Okay, so this is how the characteristic graph looks like. So let me show you the characteristic graph, and then we will come to this. Yes, so this is how the characteristic graph looks like. So this is the breakthrough voltage at which the transistor will enter in a conduction stage, and this is called as a holding current. And if you apply the gate current, so the SCR will turn on for the SCR will turn on for lesser anode to cathode voltage, and thereby the current increases. Whereas in the reverse bias condition, it acts like a normal diode where a very small leakage current will flow, and at some point after the breakdown, so there is a huge flow of current that is due to avalanche breakdown that you can see at this point. Anyway, so now let us come back to our whiteboard here. So now we will look into the two transistor model analogy, switching action of the transistor. Or before going to the switching action of the transistor, let me write the circuit of, just let me save this before. This is page 13. So now, for example, I'll be applying a DC voltage. So you can apply the DC voltage as well as the AC voltage for this SCR. You can also apply the AC voltage as well. So there might be a load connected at this point, or we can directly connect this, and here we'll be connecting the current limiting resistor, and then I'll be connecting so this here, this is the gate voltage, so I'll be applying, so this is the current which is entering here, this is the gate current, so this is IG, so this is anode, and this is cathode. So now this might be a current limiting resistor, so this is VAK, anode to cathode current. So just a minute, hold on. Sorry for that. So now what happens if this part, if there is no gate, if this VG is equal to 0 or the gate current is 0, so it means we need a very high amount of VAK to make this SCR on. So so if you want to turn on the SCR to at a lesser voltage, then we can apply this gate current to say 10 milliamperes or 20 milliamperes based on the rating of the SCR, how it is manufactured. So based on that we can do it. So once we apply the gate current, so for the lesser voltage, so rather than So suppose without gate current it might turn on for 300 volts. So with gate current it may turn on say at 150 volts, or it may turn on even at 100 volts. So we can start conducting this SCR at lesser and lesser voltage if we apply this higher and higher gate current. So once this SCR is in the on state, so then what happens if I disconnect this gate voltage or the gate current, so still the diode is in the on state, so still there is a flow of current from anode to cathode. So the gate doesn't have the control over the SCR once the SCR is in the on state. So then we require a different process to turn off the SCR, so that it might be a natural commutation process or it might be a forced commutation process that we will going to discuss later. Okay, so now we will see this. Let me save this page and come back to page 14. So now let us write this two transistor model. Switching action. So now we will see how the transistor will remain on even if we remove the gate current, so that we can see by switching action. So let us draw the two transistor model for this case. So as we have seen before, we need two transistors, that is PNP and NPN transistor, and this we connect it to ground, and here we can consider that we applied the voltage V, and this is E1 and this is PNP transistor, this is NPN transistor, this is NPN, and this is a PNP transistor, and this is our gate current. So either we can connect to a potential or we can connect this to ground. So this might, I'll write like this. Let me clear this and write neatly. Sorry for that again. So this is the ground. Okay, so this is my VG point. So this is my T1 transistor, this is my T2 transistor, and this is my IB1, and this is my collector current. IC2 is equal to IC0. So IC0 is the leakage current, T2, and this voltage from here to here we call it as VBE, base to emitter voltage, VB2. Then this current is, I call it as IB2. So this is how the transistors, two transistors, that is PNP and NPN, are connected back to back. And this current I call it as IC1, the collector current. Okay, I think we have written all, and the current which comes here, this is IK, is equal to IA when it is on. Okay, so now let us analyze this. So let us assume that we have not connected, so we have not connected the gate voltage. It means now what happens, we have connected this ground, so the gate voltage is equal to 0 volts. So at this 0 volts, what will happen when you apply this voltage here across the anode terminal? So this is nothing but IA. Then the here the base current IB1 is not equal to IC2 because this transistor is in the off state. So when Vg is equal to 0, the transistor T2 is in the off state, so which means the emitter base junction of T1 is reverse bias. So therefore the IB1 is equal to IC naught minority, which is a minority carrier, which is minority current carrier, which is very too small to turn on the SCR. So it means we can write here that is IA is equal to IB1 is equal to, this is IC naught, which is negligibly very small, so it means the SCR will remain in on state. As we connect this, so let me remove this point here. As we connect this voltage, means we have applied the gate. So when we apply the gate current, so what happens, so now this IB2 has got sufficient current to turn on this second transistor. When the second transistor is on, so it means this IC2 is equal to IB1. Once this IB1 is equal to IC2, so it means then the transistor T1 is also on. So then the transistor T1 is on, and thereby the current starts flowing in this way, and then it enters this, and it comes, then IK is equal to IA, and thereby there is a small base current which is flowing like this, and this is when IB1 is equal to IC2, so I2 turns on and causing a large collector current to flow, and this in turn will increase IB2. So as this IB2 increases, causing this as a regenerative process, so it means it is in a loop, it's a regenerative process. So it means even if we disconnect this portion of the gate, so what happens, so there is a large amount of base current at the transistor 2, and thereby which is equal to the base current of IB1, so that keeps the transistor T1 on as well as the transistor T2 on. So thereby the current will flow from the transistor T1 emitter to the emitter of this transistor T2, and thereby there is a flow of current from anode to cathode. So this is how the transistor switching action takes place. Now how do we turn off this once the SCR is on? So there are two processes of commutation, so that we will see in the next graph. So let me save this as page 15. So let me come back and make it new. So commutation process. So there are two types of commutation. So first one is, so the first one is a natural commutation, and the second one is the forced commutation. So natural commutation is one process where, for example, so let me come back to this diagrams which we have saved here. Not this one. Yeah. So let me come back to this diagram. So in this diagram, rather than applying this DC voltage, if we apply the AC voltage here at this point, so let me rewrite that diagram here. So here, if rather than the DC voltage, if I apply an AC, a very high AC voltage, so still this SCR will work. Now let us consider like this. Sorry, the diagrams are not very clear. So we have the gate current which is connected, so I will not go in much detail because we already explained this. So there is a gate current. So now an AC voltage is applied, VAK, now it is in terms of AC, so this will be positive and negative. So now what happens, so during the positive cycle, this diode is on. So during the positive cycle, what happens? We will apply the gate current, and this SCR is on. There is a flow of current. So then we will get this like this. And during negative cycle, at this 0 point, what happens? Then the SCR does not conduct in the opposite direction. SCR does not conduct in opposite direction. So SCR will only conduct from anode to cathode. It does not allow the current to flow from cathode to anode. So that is why, let me delete this. So now in that case, in a natural commutation process, since it is an AC voltage, automatically the SCR will turn off. It will come to off state during negative half cycle, and during next negative positive cycle, if the gate current is given, then it starts conducting. Now here there is one more funda. I can control this conduction process. Rather than conducting for the entire cycle, I can conduct for just the portion of it. For example, if it is like this, rather than conducting at this point, I will start conducting at this point like this, and I'll get a waveform like this. So how is that possible? Because when this positive rise, I do not give the gate current. I'll slightly delay the gate current to turn on. So this, I call this difference, I call it as alpha. So alpha is a parameter which I can control the on and on period of an SCR, means how much portion of the waveform I can control. That we call it as a triggering point, that is alpha. Okay, so this is one more advantage of an SCR. I can control the amount of current that can flow even with this triggering point alpha. So this is about the natural commutation. So what is a natural commutation? In natural commutation, automatically when the anode to cathode voltage comes to 0, it means the SCR will turn off. So this we call it as a natural commutation. So what is a forced commutation circuit? So in forced commutation circuit, we have to apply a large negative voltage or a large voltage in an opposite direction. So that will make the transistor in off state. So let me write that circuit. So before that, let me save this page 16. Okay. So for that, we can say this. So here I have my SCR. So for this SCR, I'll connect to a transistor, and from a transistor, I'll connect to an voltage source, and that is, so this I'll call it as VB. Okay, so there is a load resistor which is here, and it might be connected to ground at one point. So this, let me call it as R. So this is our gate IG, gate current. So this is the V, and this is the IB. So this is an NPN transistor. So now this is a forced commutation circuit. In forced commutation circuit, what happens? So now you applied the gate current, and anode to cathode voltage is applied. Now the current is flowing. So now the current is flowing from anode to cathode. So now what happens in this case, if you want to turn off this SCR, even if I remove this gate current, what happens? Still the SCR is in the on state, so it will not come to an off. So to make this transistor to off, I have to apply a reverse current. So reverse current, how do I get it? So there is an voltage source that is connected to a transistor. Once I give this base current, transistor is on. Once the transistor is on, this voltage source will turn on. So then what happens? This voltage source, a large amount of voltage source is applied in a opposite direction for a small amount of time. So then the current flowing through this SCR will be compromised, and then the SCR will comes to 0 or comes to a halt, or the SCR will turn off. So hope you have understood this session on SCR. So we have discussed on the SCR construction, the two transistor model, and we have explained how the switching action takes place with the two transistor model. We explained the characteristic graph, we explained the commutation process. Okay, so please, if you're not understood, go back to the session and see through it. So thank you for watching this session. Take care.